for continuing to attend. So let me just briefly recall what we discussed yesterday. So we discussed minimal resolutions. So whenever we are given a ring of polynomials and a finally generated graded module over this ring, then we have a minimal free graded resolution, which looks like that, which is basically obtained by iterating approximation. So we approximate M by a free module and then the kernel by another free module and so on. And this minimal resolution is unique up to isomorphism, so the factors are uniquely determined, which gives some numbers which are called the graded Betti numbers of the module. And we organize these graded Betti numbers in a table, so that if we take the alternating sums on these diagonals, then and we call these sums by capital B, then these B's can be recovered from the Hilbert function. But we have seen an example where the graded Betti numbers cannot be recovered from the Hilbert function. So they determine the Hilbert function, but we cannot go in the other direction. And let me just point out to an important property of these graded Betti numbers, which is semicontinuity. In some sense, these graded Betti numbers behave like dimensions of some cohomology groups of coherent sheaves. And in a certain sense they are. We will see at the end of the lecture that they can be interpreted in this way. But what is semicontinuity? So whenever we have, suppose we have xt or t in t, a flat family of projective varieties. So we know from Hartshorne's book, no, I should say, actually I always wondered which is the correct pronunciation. It's either Hartshorne or Hartshorne. And then I learned that Hartshorne is the book and Hartshorne is the person. So we should say either we know from Hartshorne or from Hartshorne's book. I think that's the correct English expression. So flatness is equivalent to the constancy of Hilbert polynomials. So Hilbert polynomials are the same. But we require a little more. So suppose the Hilbert functions are the same. So under this hypothesis, the beta ij of xt, where we either take the graded Betti numbers of the ideals or of the homogeneous coordinate ring, they are basically the same thing, are upper semi-continuous.
So sorry, in a flat family, the Hilbert functions are not necessarily the same in general?
No, I will give you an example.
Okay.
Yeah, so here's an example. It's only the Hilbert polynomials that are the same, but Hilbert functions can vary. So if you take, so I think that, yeah. So if you take again 4 points in P2. We discussed this yesterday, but we have now two different cases to discuss. So the first case is when they are general points, and the second is when they are, let's call this X, when they are on a line. So we have 4 points on a line. So these are very special points. If we look at the graded of the Betti tables of the homogeneous coordinate ring. So yesterday we discussed the Betti tables of, so if we take 4 general points, then the ideal is cut by 2 conics. So we have, for Sx, we will have one generated which stands for S, then we have 2 conics, and we have one relation between these conics. So that's the Betti table of in the first example. And in the second example, we start with the generator, which is S, the first factor, but then we have a line. So they are on a line, so we need one linear generator. And since we have 4 points on a line, we also need a quartic. So we need a quartic in the ideal. So the ideal is generated by a linear form and a quartic. And this is and they only have one trivial relation. So we see that in this case, beta, what is this? So this is beta 1, 2 equals 2. And in this case, beta 1, 2 equals 0. So this one is strictly lower than the other one. But that's because the Hilbert functions are different. So in the first case, the Hilbert function was 1, 3, 4, 4. And in the other case is 1. So they are on a line. So there is a line in the ideal. So this is 2, 4, 4. So the Hilbert functions differ. That explains. So somehow there is a subtlety here. Whenever we have a 0 on this column, the column of the generators of an ideal, this doesn't mean, so here the fact that we have a 0 in the Betti table doesn't mean that we don't have conics at all in the ideal. In fact, we have conics. It just means that we don't have conics in a minimal set of generators. So this means the fact that we have a 0 here means that all the conics are multiples of this linear form. So this, more precisely, if we look at, so again in this case, if we look at I2 of x, this will be just the image. So that will be isomorphic to, let's call this form by L. So this is K times L. Tensor, we are in P2, so we have V of dimension 3. So actually the dimension of I2 of x is 3. Whereas here the dimension of I2 of x is 2. So the fact that the graded Betti tables are not upper semi-continuous in families which don't have, when Hilbert function might jump, might be a little counterintuitive, but this is because of the nature of Betti numbers. So once again, having a 0 here doesn't mean that we don't have generators in certain degree. It means that in that particular degree, all the forms are generated by forms of lower degree. That's the meaning of Betti numbers.
In the family, you don't have to fix some embeddings of each T.
No, we fix embedding. So this is everything relative to an embedding. So when I said projective varieties, this means that we also have embedded.
Both cases embedded in some big projective.
Well, it could be in a projective bundle over T or something like that. So every fiber embeds in a projective space. But flatness is the constancy of Hilbert polynomials. Like here we have 4 points, so this means that we have a flat family because the Hilbert polynomial is constant, is 4. So yeah, I wanted to point out to this difference between the dimension of the graded piece of the ideal and the Betti number. So there is a difference. So here, if we just look at the dimension of I2, then we see that the semi-continuity holds indeed. So this is lower than this one. But for the graded Betti numbers, it doesn't hold. Okay, but that's because the Hilbert function is involved. Let me just recall what we discussed yesterday again. So there was an example which was a very important example of minimal resolution when M is the residual field, or S, S mod out by the irrelevant ideal. So that, in this case we have a minimal resolution which can be expressed in terms of tensors like S, V tensor S of minus 1, wedge 2 of V tensor, so this is over K, S of minus 2, and so on. The last one would be wedge n plus 1 of V tensor K over K S of minus n minus 1. So as usual, V is the span, the linear span of the variables. And this is the, so this goes to 0. This is called the Koszul complex. And it's a very important complex because out of this Koszul complex we can recover actually all the minimal resolutions. Eisenbach actually calls this complex the mother of all the resolutions. And we will see in a moment why. Because so that Koszul complex computes all the minimal resolutions. In the following way, let's go back to the definition of the minimal resolution. What is a minimal resolution? We have an exact complex, and whenever we mod out this complex, we mod out the irrelevant ideal, all the differentials will become 0. So if we want to compute these numbers, beta ij, all we have to do is to look at this complex, reduce modulo the ideal x0 xn, and then compute the dimensions. So this means that we tensor by the over S by the residual field. But then what do we get when we have an exact complex? When we have a resolution, we tensor with another module and take the what we get in the middle. So this is exactly the Tor.
Can you repeat that again?
Yeah. So what I'm saying is that beta ij is Tor of Tor I of M and S over x0 xn j. So if we look at this object, Tor I, the Tor, since we work with the with graded, this is a graded object, this is a graded object. The Tor is naturally graded, so we have a grading on the Tors. How are the Tors obtained? We take a resolution, a free resolution, or a projective resolution in general, but here we work with free resolutions of this object. We twist by this object, we take the cohomology, and then we look at the graded pieces. Right? That's the definition of the Tor. But if we twist by the residual field, then all the differentials will become 0. So taking the cohomology gives nothing, gives just what's in the middle. And what's in the middle will be graded by the grading will be given by this. So it's exactly the dimension of what we get in the middle. right? So if we twist S of minus j by k, we just get k, just with the shift in the grading. So k is all concentrated in this degree 0. If we twist by minus j, it will be concentrated in degree minus j.
So I still don't understand the remark how this Cazul complex is computing the minimal free resolution event.
Yeah, it comes now. So yes. Now the Tor functors are symmetric. So whenever either we compute the Tor starting from a resolution of m or from a resolution of the other object. So Tors are symmetric. And since it's symmetric, we can start with this resolution of k and twist it by m and take homology. And we get the same object. So in particular, it's also obtained by twisting the Cazul complex with m and taking homology. Correct? So in this case, if we twist by m and we take homology, we get another nice object, which is called the Cazul cohomology of.
So that gives us the Betty numbers back, but how do you get the maps?
Yeah, I will write them down in a second. So that's the Cazul cohomology. What are the maps? That's a very good question. Thank you. So what are the maps? So the maps are given in as follows. So suppose we want to compute Tor I. So Tor I will be computed here in the ith term of the resolution. So we have to focus on wedge I. So we have to focus on wedge I, V, tensor something. This comes from wedge I plus 1, V, tensor something. And it goes to wedge I minus 1, V, tensor something. And now let's look at the what we get here. So that's m of minus I minus 1 over S. This is m of minus I. This is m of minus I plus 1. And now let's take the jth graded piece. So that will give wedge. And let me look at the I plus jth graded piece. Which will mean that here we look at beta I plus j, or here we look at Tor I plus j. If we look at this I plus j graded piece, it means that we have here wedge I V tensor mj. It comes from wedge I plus 1 V tensor mj minus 1, and it goes to wedge I minus 1 V tensor mj plus 1. What are the maps? So the maps are induced by the maps in the original Cazul complex. They are just obtained by tensoring with m. So the maps are the following. Working in coordinates, the first map will send x I0 wedge x I is not a very good k0 ki tensor some element, let's call, I don't know, little x, will be mapped to the sum minus 1 j x k0 wedge. Here we remove what's on the jth position, xki, and we multiply this by xkj times little x. Let's convince ourselves that this is correct. So here we have I plus 1 decomposable multivector. So it's in wedge I plus 1 of v. That's of degree, so our little x is of degree j minus 1. When we multiply by a variable, it will increase the degree by 1, so it becomes of degree j. And this is a decomposable vector in wedge I. And the same is defined also the next one. So the next one is defined in a similar way. So that's the causal complex. So the cohomology at the middle term is denoted by Kij of m and v. We want to emphasize the variables. Why do we want to emphasize the variables? Because let me just comment. If we take W, a subspace in V, so that the symmetric algebra of W is a sub-algebra of S, and M is also a sim W module, graded module. So we might restrict the scalars. So this is allowed. So we want to emphasize with which variables do we work. Okay, so that's why Eisenbach stated that this causal complex actually generates all the minimal resolutions, because out of this original causal complex we can get by tensoring all the other minimal resolutions. So the moral is that the dimension of Kij of mv, so that was obtained by taking the ith plus j graded piece. So this is just beta I plus j. Consequently, if we are able to compute these maps, which are not easy to control, so that's another issue, but if we are able to do so, then we can compute the Betti numbers of the graded Betti numbers of the module. Okay. Let me introduce some more notation. So what were the favorite geometric examples we will work with? So one example is when X is in the projective space, and we take M to be either the ideal of X or the homogeneous coordinate ring of X. So in this case, we write, when there is no danger of confusion, we write Kij of X for Kij of X, Sx, and V. Just to shorten the notation. Or it might also be that we have X a variety, we have L a line bundle on X, and we can take V to be H0 of L, and we take the this module R of XL to be the module of or the ring of sections in powers of L. So if L is very ample, then this is nothing but the integral closure of the homogeneous coordinate ring. So there is a relation between the two. However, this seems to, now it depends. So people working in which are more which are closer to algebra prefer to work with this this module. Those who are closer to geometry prefer to work with this module. Now it depends on the what is your aim. Or there's another version. So if X is a variety, in this case let me set the notation. So in this case Kij of Rx L V is denoted by Kij of XL. Or it might happen that, so there is a version if we take W not to be the whole space of sections, but, or let's put V just a subspace of sections, then we write Kij of X, L, and V for the Kozulko homology. Of RXL. And again, if X is a variety, L is a line bundle, and F is a coherent sheaf on X, we can take this RXFL to be the module of sections of F twisted by powers of L. And in this case we denote by Kij of X, F, L, or if V is not the whole space of sections, we also want to write this down. So that's about the notation. So I hope it's not too, the notation is not too heavy, but it's the notation which was originally introduced by Mark Green. So now what's the goal of syzygy theory? The main goal of syzygy theory is to try and extract geometric information out of these possible modules. So what kind of geometric information is hidden in these Kozulko homology spaces? Or if you wish, since their dimensions are, at least for these examples, are graded Betty numbers of varieties, what kind of information can we extract out of the graded Betty numbers beyond what's given by the Hilbert function? Because the information given by the Hilbert function is just about how it's behaved, our variety, with respect to hypersurfaces. That's what Hilbert function gives. The hope is that maybe we can also detect how this is behaved with respect to lower dimensional varieties. For example, if we have some points in a projective space, can they, in a big projective space, can they be put on a rational normal curve? That's one kind of question which Hilbert function does know how to answer, but can be approached by syzygies. But there is a lot of more information, geometric information hidden in these graded Betty numbers, and we will see, probably, yes, we will see that today. Okay. So before going further, let me just point out the following fact. So if M and P are S-graded, finally generated S modules, and this is a short exact sequence, then we have a long exact sequence induced at the Koszul cohomology level, like Kij of MV goes to Kij of NV goes to Kij of PV goes to Ki minus 1 J plus 1 of MV, and so on. So these sequences are very useful if we want to compute the Koszul cohomology of a given module. If we can put this module in a short exact sequence, and we can control the Koszul cohomologies of the other modules, then we are basically done. So together with the observation that Kij of S itself, seen as an S module, is 0 except for K00 of SV, which is K. In this situation, we obtain Kij of X. So the Kij of a homogeneous coordinate ring is isomorphic to Ki minus 1 J plus 1 of the ideal. So we can jump from one. So whenever we speak about Koszul cohomology, we either choose the ideal or the homogeneous coordinate ring is basically the same thing, up to modifying the weight and the degree here. Which is to say that if we look at the minimal resolution, if we put here the homogeneous coordinate ring, we are forced to start with S, and the image or the kernel is the ideal. So if we just cut here and take the image, we get the ideal. That's somehow the explanation. Okay. So how to compute? So this theoretically that's a very nice description, but in practice, since multilinear algebra is involved, these maps are very hard to compute and control. So how to compute? So the basic question is how to compute Koszul cohomology. Since we want to try and answer, at least in some cases, this question. So the question is how to compute Koszul cohomology. Of course, I suppose that we are in one case in which the minimal resolution cannot be computed directly. Because if we can provide the minimal resolution, then we are done. We don't need to compute the Koszul cohomology anymore. But let's suppose that we are in the following situation. We want to find a minimal resolution. We have no idea, no clue what this is. Then we apply Koszul cohomology. We try to compute Koszul cohomology. It's the same magnitude of difficulty. And then we try to do something else. So we need techniques to compute these Koszul cohomology groups. And there are several approaches. So one approach is using vector bundles, or the two approaches are actually using vector bundles. But one is using vector bundles on the variety itself, and the other one, which is more recent and due to Claire Vazin, is to pass to the Hilbert scheme. But I will discuss tomorrow the Hilbert scheme approach. Today I'm going to focus on this approach. So I have to say that I love vector bundles because my initial formation was, so I come from vector bundle theory, so I That's how I got to syzygies. So whenever there are vector bundles involved, I'm very happy. So how to relate Koszul cohomology and vector bundles? The approach, the first approach is, and the first and the last, which are going to discuss today. The first, so this approach uses the Euler sequence. So more precisely, if we start with the original with the Koszul complex, Koszul resolution of K over S, and Schiffify it. So if you Schiffify it, the free modules will turn into decomposable vector bundles, and the vector bundles are, now I'm not in the Macaulay setting anymore, so I'm going to write the arrows just in the normal way. So we start with O, Pn. Then we have here V tensor O, Pn of -1. Here we have wedge 2, V tensor O, Pn of -2, and so on. But if we take a closer look at this map, the kernel, we know what this is. So the kernel is the sheaf of differentials. So the kernel is just omega 1 of Pn. And this factors through the other map. So this map will factor through omega 1. Now what's the kernel of this map? The kernel of this map is the sheaf of differentials of degree 2, omega 2 of Pn. And the next map will factor through omega 2, and so on. So we go all the way to the end. So we split this Schiffified Koszul complex in smaller Euler sequences which look like omega p plus 1 or Pn, V tensor O Pn minus p minus 1 goes to omega p, Pn goes to 0. Sorry, there's a mistake here. There should be a wedge p plus 1. V. Okay. And now what do we do if we have x in Pn? We can restrict these sequences. So if we have x in Pn, we can restrict the sequences, and that's the let's also put L to be O x of 1. Let's put OML to be omega 1 of 1 restricted to x. There's the notation introduced by Rob Lazarsfeld. Then what do we get here if we twist by so restrict the sequence and twist by say, or let's keep the same notation, LP plus Q, we will get precisely the following sequence: wedge p plus 1 ml, tensor L q minus 1, wedge p plus 1 of V, tensor L q minus 1 again.
Sorry.
Yes?
If I want to try and understand this sequence geometrically, what I was hoping to do was just think of this over some open neighborhood. So
Yeah, that's how the original Euler sequence is obtained, actually, how it's constructed.
yeah, but unfortunately for me, the arrows are going the direction opposite I would want them to, because closed forms are exact, and you have the natural exterior derivative on differential forms, and you're somehow splitting this locally, but it's going the other direction. Maybe this is not a good way to try to think of it.
No, it's in the right direction.
No, I'm sure what you're doing is correct. I'm just trying to get some intuition for it and failing. So, like, what would could you just, I mean, if you don't want to do this, you don't have to, but what would this map from lambda 2 be, tensor O of minus 2 to lambda to omega 1 be, kind of locally?
So, let's see, let me see if I can write it locally.
Because we know what the map above it is, so...
This one?
No,
or this
know
one?
What the horizontal map is.
Ah, this one, yes, we know it, yeah.
That we know very well.
So
so I'm just trying to understand the factoring of that.
so the claim is that this factors through omega 1. That's can we write this locally in affine coordinates?
Why,
yeah.
You know, it's a good way to understand that.
Yes. Let's try to do this after the talk, right?
Okay.
Yeah, we can discuss this right after. Yeah. Okay, so if we restrict it and we twist by these powers, then we get wedge P of ML tensor LQ goes to 0, correct? And then we can take global sections H0, and then we get a sequence wedge P plus 1 of V tensor H0 LQ minus 1 to H0 of wedge P ML tensor LQ, then goes to H1 of wedge P plus 1 ML tensor LQ minus 1, goes to wedge P plus 1 V tensor H1 of LQ minus 1, and the observation of Rob-Lazar's is that KPQ of X and L is precisely the co-kernel of this map. Let's call this alpha P and this beta P. Is the co-kernel of alpha P, which is the same as the kernel of beta P. So whenever we want to compute causal cohomology, so actually the statement is that because this piece already appears in the causal complex, the statement is that this H0 is the kernel of the causal differential, the next causal differential. That's that's his statement. So if we are in conclusion, if we are able to control these maps, then we have a hope to compute the causal cohomology. And I'm going to give one very quick application, which is duality for curves. Well, duality holds in general, but it's more complicated since we... I'm going to keep this on the board for the discussion after. So, theorem, duality for curves. If we have C a curve, L a very ample, can be also globally generated. It makes sense because instead of restricting, we can just pull back these sequences. So the whole definition makes sense also for globally generated. But the most important cases are for very ample. a vector bundle on C, and we are looking at Kij of C, E, and L. So E can be trivial. So if E is trivial, then we simply have the Koszul cohomology of C. Then this is isomorphic too. Let's consider that H0 of L is R plus 1. That's isomorphic to K R minus I minus 1, 1 minus J of C, K tensor E dual, L, and everything is dual here. Let's see a short proof of that. So what is we should also remark that the theorem has a version for this KPQ XFL. So when we compute the module of sections of F tensor the powers of L, that's the co-kernel, again, is a co-kernel of a map alpha prime P, where this is just obtained by tensoring with F here. So if we just tensor by F and take alpha prime P, is obtained similarly plugging F in. Okay.
The index should be R minus I minus 1 and 2 minus J.
Yes, thank you. Thank you very much. It's 2 minus J. Yeah, we will see that in a moment. So Kij, what is Kij of CEL? This is the co-kernel of the map from wedge I plus 1 V, let's call V to be H0 of L. Tensor H0 E tensor Lj minus 1 to H0 wedge I ML tensor E tensor Lj. Okay, and now we dualize everything. So if we take the duals everywhere, that would be the kernel dual of a map which goes from the dual of this space, H0 of wedge I ML tensor E tensor Lj dual to wedge I plus 1 V dual tensor H0 E tensor Lj minus 1 dual, so everything dual. And now we simply apply Serre duality. So by Serre duality, H0 wedge PML tensor E tensor L, sorry, that's not P, it's I tensor J dual, that's isomorphic to H1 wedge I ML dual tensor K tensor E dual tensor L minus J. But wedge I ML dual is isomorphic to wedge ML is a rank R vector bundle, and the determinant is minus L. So that would be just R minus I ML tensor L. Hence this is H1 wedge R minus I ML tensor K tensor E dual tensor L1 minus J. So that's the first one, the first guy. The second one is V is of dimension R plus 1. Hence wedge I plus 1v is isomorphic to wedge r minus I v. So that's the dual. So we can replace the first space by what's written there, wedge I plus 1v dual by wedge r minus 1v, and the last one, h0 e tensor lj minus 1 dual. This is isomorphic to h1 of k tensor e tensor L1 minus j, and that's it. Now if we replace everything in there, so we have a kernel of a map from h1 to wedge r minus 1 iv tensor h1, and the kernel as stated here with the small modification that we have to plug f in everywhere, we get exactly the second. So that's the second group. The shift comes from the fact that we need here we compute kp1 and we have wedge p plus 1. That's why we have. Okay. So that can be very useful. And one last thing for today. Is shift regularity. So shift regularity can be computed from Koszul cohomology in the following way. For this I'm not going to give a proof, but I'm just going to state it. But the proof can be, this fact can be proved in a similar manner using this kernel bundles. So let me recall what's the regularity. So f on x in Pn is called M regular in the sense of Castelnuovo method if hi f tensor L m minus I equals 0 for all I bigger than 0. Because of SER vanishing, any sheaf is M regular for some M. And the minimum M is called the regularity. So the regularity of F is just the minimum of M such that F is M regular. So regularity is a very important notion. For example, if you want to construct moduli spaces, we need regularity. And the interest is that to have, since any f is M regular for M big enough, the interest is to have regularity as small as possible. So the smaller the regularity is, the better the sheaf is in a certain sense. And now the proposition is that the regularity of f is the minimum, also the minimum of all M such that kp m plus 1 of x f, and let's call L to be O of 1 and L equals 0 for all p. Or if you wish, is the maximum of all M such that there exists a p with kpm of x f L different from 0. And that's particularly useful for f equals Ox, in which case we get the regularity of the variety. So the regularity f is Ox will give just kpqs of x and L. In this case, the regularity actually is the size of the Betti table. So the number of rows in the Betti table is the regularity of the variety. That's also why another reason why we write the Betti table like this, because otherwise we would have compute the regularity on the diagonals, which is not very nice. But having this interpretation, it's somehow more intuitive. And yeah, for example, if x is a curve and L is non-special, then the Betti table will only have one and another 2 rows, and that's it. Yes, and I think I will stop here for today. So I'm a little bit behind the schedule. Tomorrow I will start discussing. So I was supposed to discuss syzygy schemes today, but I will discuss them tomorrow. Because tomorrow, what is the plan is to try to relate geometry and syzygies, and to see how we can get syzygies out of geometry and vice versa. How can we get geometry out of syzygies? Okay, thank you very much.